Hey everyone, this is Brian. Welcome to week 8 of CSC 143. Hope you had a great weekend. I don't actually have any announcements today, so I want to go over some recursion tips that I'd like you to take in when you're working on your Project 3, which is of course going to be due next week on Wednesday. Project 3 goes over a lot of recursion problems, and I like to say that once you figure out one of them, you figure out all of them. But what I've noticed over the last couple of years when teaching this particular topic is that students will run into a lot of pitfalls that they'll turn in as their project submissions that are actually errors in terms of writing recursive functions. So I posted a list of these pitfalls on Piazza and how to overcome them. And I want to spend the time today in this introduction to go over these potential problems and how you can resolve them. So the first problem I want to talk about is called dropping the ball. That's like a thing I made up, but you kind of hear that every now and then. And I say it's dropping the ball because it's a problem where the recursive call doesn't actually get saved anywhere. The ball has been dropped. Let's take a look at this example of a sum function that sums up all the values within a given tree. I have a root node as my argument, and you can kind of imagine the root structure looking at like having a payload and having a children list of child nodes. My base cases are pretty simple. If there is no root, return 0, which is a sensible default for a sum function. If there are no children, then just return whatever the value of the root is currently holding on to. Otherwise, we will compute the total value of this tree by taking in the value at the root and then adding on the recursive calls to the sum of all the children. So I start out with my total as root.payload, the value at the root, and then for every child in my children list, I'll recursively call sum of that child and then return this total value. We have actually dropped the ball in this recursive call. This is a recursive function because we're calling sum again, but you'll notice that we're not actually doing anything with the return value of the sum call. We're kind of treating it like a void actually. I call sum of child, but I don't do anything with it. I don't save it to a variable, I don't add it to my total. It's just a call and it's actually wasted because the return value never gets saved to anything. So this is dropping the ball. We have computed the result of the recursive call. We've gotten this ball and we've dropped it because we're not saving that recursive call. So whenever you're writing these recursive functions, make sure that in order to form that composite solution, you're actually taking those subcalls and combining them into a collective result to send back to the original caller. So the way to fix this up is we need to save the total value. We need to save the recursive call to sum inside the total value. Here I'm just adding it to my total. That way, whatever this recursive call gives me, I'll add it to the total value I'm going to return, and then I'll return that in the very end. That is a working recursive function. The next pitfall I want you to avoid is these redundant calls. And this can happen when it seems very easy to just call the function as part of a condition, and then changing your recursion logic based on what that condition result is. But the outcome is that you might end up calling the recursive function more than once because you wanted to evaluate a condition first and then actually evaluate the composite, the subcalls to form that composite solution. So let me give you an example. Here's my sum function again. Let's skip the base cases because those are pretty simple. And let's suppose for a moment that I tried to like optimize my solution by saying, okay, if the sum of this particular child is 0, just skip that child. In some of your recursive calls, this is going to look a little bit more complicated. Typically on like the path functions that I have for your project 3, you're probably going to need something that looks like this, a conditional recursive call that's based on the result of whatever recursion returns. But if you'll notice here, I might actually end up calling sum twice. Let's suppose sum of child is returning something not 0, so I skip this continue step. I actually call it again here when I add it to my total. So let's say sum was like 5. Okay, that's cool, I figured that out using recursion. But then down here, I have to call sum again, even though I already called sum previously and I knew that it was 5. So this is what I call a redundant call. You already know what the sub call is going to produce, so why bother doing it again? This requires traversing the entire tree another second time. So I want you to actually fix this by saving the result of this sum call in a variable the first time you did it. So what I'd like to do is, let's say I had a line here that was like result equals sum of child. Then I can ask if the result is 0, continue. I don't have to do any extra computation there. Otherwise, add the result onto my total. That way there's a only one recursive call to the sum function, and I can use it twice inside my conditional here and inside my total computation on this line. The third issue I want to have you avoid is the mistake of doing an early return. So here's my sum function one more time. And in this sum function, once again, I'm going to go recursively compute the result of my children so I can add them to my total. And rather than actually doing that add to the total, I'm actually going to return the sum of the child. So this is a mistake because remember, the result of this top level recursive call to sum needs to be the composite solution of this subproblem, which includes the root node and all of the children combined. Here, I have started to traverse all my children performing iteration, but I actually return right away. So I'm actually only really getting the recursive call to one child, not the collective call of all these children combined with my current root. This is a mistake you want to avoid, but it's a very easy pitfall to run into because sometimes it's very easy to get confused with the value you're actually supposed to return, which is the composite solution to all these subcalls, and instead return a more specific solution to just one child within this tree. What you should end up getting in most circumstances is test failures when you run into this. But there's also some weird circumstances where this will actually pass on certain tests. For example, if I have a tree that's entirely nodes composed of 0, the value, summing up all those nodes is going to give me 0. So in a way, this technically still works because 0 is going to be equal to the sum of any child, and it just so happens that starting from the root node, the sum of the entire tree is also 0. So I want you to avoid doing this. Be very careful about what you return and how you actually compute that returned total value that is that composite solution from all the recursive calls to the children of this particular location and whatever base cases you have at this particular node in the given tree. Okay, so I do talk about these in writing here, so I do encourage you to review this Piazza post and take advantage of these tips moving forwards in your implementation so you don't make these kinds of mistakes. Cool. Thank you so much for listening. Have a wonderful week and enjoy the video. Hey everyone, this is Brian, recording a video lecture for CSC 143. In today's video, we're going to be learning about sorting, merging, and heaps, a new data structure. Let's talk about sorting first. Sorting a list is an old-fashioned problem with several well-known solutions. Sorted lists have a number of useful properties. A sorted list can be binary searched in log of n time, rather than linear searched in O of n time. Remember, the binary search algorithm is one that we covered last class, where we have the search space remaining with every single step of the search. By nature of the list itself being sorted, we can jump to the middle of the list and then decide whether to look at the front of the list or the back of the list with every single step that we make. Eventually, we're going to narrow down our search space to be one element, which is either going to be the element we're looking for or not the element at all. This is going to be much better in log of n performance than the linear time O of n performance. Merging two sorted sequences into a single sorted sequence can be performed in O of n time, linear time. We'll learn about this technique pretty soon. Finding the minimum and maximum values in a sorted list are always going to be O of 1. This is pretty intuitive. Just look at the head and the tails of the list. And perhaps, subjectively, sorted lists are nice and interesting to look at. We look at a lot of sorted things, whether it's from statistics, on polling, or news sites, or news feeds like Twitter. We want to be able to absorb content in a way that is arranged in an order that is most relevant to us. Let's talk about some naive sorting algorithms, as I like to call them. I call them naive sorting algorithms because they're ones that you can come up with on your own pretty easily, and perhaps a small child could do the same if you ask them to sort a deck of cards, for example. Selection sort is perhaps the simplest sort there is. Here's how it goes. We'll divide a list into two parts, sorted and unsorted, where the sorted partition starts empty. We will search the entire unsorted partition for the minimum element among the unsorted partition. Then we will append the minimum element from the unsorted partition to the back of the sorted partition. Then we're going to keep doing that over and over again until the unsorted partition shrinks to nothing and the sorted partition grows to consume the entire list. Let's take a look at how that works on a whiteboard. Here is my list of 5 values, 5, 2, 1, 4, and 3, and selection sort tells us we should go find the minimum element and then place that at the end of the sorted partition. If we start out looking for the minimum element among these numbers, the minimum is going to be 1. Our sorted partition is completely empty, so the 1 value is going to take place at the beginning of the sorted partition. We'll shift that into the spot where 5 currently is. To make that an O of 1 operation, we'll simply swap whatever is currently at the end of the sorted partition into the place of the value we just found. So 1 and 5 are going to swap here. Next up, we have divided our list into a sorted partition on the left, which just contains 1, and an unsorted partition on the right, which contains the values 2, 5, 4, and 3. If we look down the entire unsorted partition, we see that 2 is the next smallest value, and it's already in the right place, so we don't have to do anything. We look down the unsorted partition again, and we find 3 is the next smallest value in the unsorted partition. So I need to swap that with the end of the sorted partition, which currently stores the value 5. Next up, I have values 4 and 5 in my unsorted partition. 4 is, of course, the smallest value among those, so that stays in the right place. Then my unsorted partition ends with just one value, which is 5, which is already in the right place, so I don't have to do anything. That gives me a sorted list, 1, 2, 3, 4, 5, and I've done it in n squared time. How do I get that n squared computation? Well, every time I look down the entire list to go find the minimum value, such as when I did in the very beginning to look for the value 1 here, I then had to look down the entire list with every single successive step to form the remaining elements of the sorted partition. So one way of thinking about this is we have to walk the entire list, which is O of n steps, with every single element inside the list, of which there are n, so n times n gives us n squared performance. Now let's go take a look at how that is actually written inside code. Let's go visit sorting.java. Okay, so here's my public class sorting, and it's just simply a container for the static selection sort method that, as you can imagine, is going to perform a selection sort on a linked list of integers. This list node here is just a container for an integer value and a reference to a next node. Okay, we'll start out with declaring a reference to the head of the unsorted partition, which represents the node succeeding the sorted partition. So this essentially divides our list into two parts: the sorted partition and the unsorted partition, which starts at the unsorted head value. And of course, the entire list is going to start as unsorted. We're going to move the unsorted partition, the reference to the head of the unsorted partition that is, up till the very end of the list when the reference finally becomes null, which is of course referenced by the tail node of the entire list. It should point to null. In our quest to find the minimum value among the unsorted partition, we will start out with a default value of whatever is currently at the beginning of the unsorted partition, and we will reference that location, the node containing the minimum value, as the head of the unsorted partition. We'll make a copy of that in unsorted start, so we can start to manipulate this unsorted head value. Actually, it looks like we're going to be manipulating the unsorted start value in order to shift our reference forwards. So unsorted start is a copy of unsorted head. Then I need to scan the entire remaining unsorted space to go find the element that is the minimum among those. If the minimum value I have right now is null, or the value I found at my unsorted start is less than the present minimum value, then I will update my present minimum value with whatever's currently at my unsorted start, and then I will update the location to that minimum value by replacing it with the current reference to the node that contains it. Then at the end of my loop, I'll shift my unsorted start up by 1. The outcome of this loop here is that unsorted start will begin at the unsorted head, the beginning of the unsorted partition, and eventually reach the very end of the list. In doing so, I should go look at every value inside the unsorted partition and keep the value as well as its location where the value is the minimum value among all the remaining elements. Now that I actually have those values, I will swap the current value at the unsorted head with the value at the minimum location. So this is like in the whiteboard when we exchange the values 1 and 5. We're essentially taking an unsorted value and placing it into a different location in the unsorted partition, and we're taking that minimum value and placing it back where the unsorted partition began, such that the minimum value we found takes the place of the end of the sorted partition. Then once we've resolved another value in our list, we will move our unsorted partition up by 1 node, now that that minimum value has taken the place of the beginning of the unsorted partition. We will do that over and over again until the unsorted partition becomes empty, and unsorted head reaches the very end of the list, which represents no more list elements remaining. Then we'll go ahead and return the list. So this selection sort is going to perform a sort in place. What I mean by that is it's actually going to manipulate the values within the nodes of the list. Now, this will not actually rearrange the nodes in the list. I want to make that clear by visiting this swap method I've got referenced here. Go ahead and press the Control key and click on it to go to the definition. I've gone ahead and defined it inside list node as a helper method. Swap is simply going to exchange the payload values inside the left and right nodes that are passed to it. It will not, in place, rotate the elements, the nodes themselves. I do so by saving the left value temporarily, replacing the left node's value with the value on the right node, and then I update the value in the right node with the temporary value. So in essence, the left and right containers will stay in the same place, but they will be their internal values that they're containing will be swapped among them. Okay, now let's go take a look and verify that this works inside my sorting test file. Public class sorting test has a selection sort test. Let's kick things off with a list that simply has a value 5. Then we'll append another value to that list. 4, another value 3, 6, 1, and 0 and 2. That gives me a list containing 5, 4, 3, 6, 1, 0, 2. Definitely not sorted. Let's see what our algorithm does. When we call sorting.selectionSort and we pass in the head reference to the list, we can then validate that the values that come out of that list are going to appear in the order 0, 1, 2, 3, 4, 5 as we traverse the list. And it occurs to me this 5 here should actually be a 6. Let's go ahead and update that. Okay, great. This loop essentially says take the numbers from 0 to 6, inclusive, which of course are the numbers within our unsorted list, and validate that they will appear in that order from 0 to 6 inclusive when I look up the values at the respective indices. Okay, now let's talk about the performance of selection sort. We've discussed how the actual runtime cost is still n squared because I need to traverse the entire list to find the minimum element among the unsorted partition, and I have to do that every time for every element inside my list, which of course there are n times n gets me n squared. Stack space, on the other hand, is O of 1, which seems pretty cheap. I don't have to perform recursion for this algorithm to work. I don't have to create additional stack frames beyond the initial one that I had created for the call of the function. So this does consume a constant amount of stack space. Before I move on, I want to remark that the theoretical performance analysis of sorting algorithms tends to assume that insertion, swap, and append operations are always O of 1. Practically, we can kind of think of this as always being implemented on a linked list. Inserting into a linked list, we've discussed how that is an O of 1 operation, so long as you already have a reference to the location you need to insert to. Swap is the same way. We can exchange values between nodes in a linked list pretty easily. And depending to the end of a linked list is always going to be O of 1, given that we have a reference to that tail node, and we can just chain on an additional node value. Now let's turn to another naive sorting algorithm. This one's called Insertion Sort. Insertion Sort is similar to Selection Sort, except that it inserts values into the correct positions. Let's go over how that works. We will once again divide the list into two parts, a sorted and unsorted partition, where the sorted partition contains the first element. We will then examine the first element among the unsorted partition and insert it into the sorted partition in its correct location. We will repeat that process of looking at the first value in the unsorted partition and moving it into the right location among the sorted partition until the unsorted partition shrinks to nothing and the sorted partition takes over the entire list. Let's take a look at that now on the whiteboard. Okay, with insertion sort, I'm going to start off by declaring my first element in the list as being the first element of the sorted partition. And then these remaining elements, 2, 1, 4, and 3, are going to be unsorted. Then I will look at the next immediate value among the unsorted partition. I decide among the sorted partition where it belongs. How do I do that? Well, if my sorted partition is guaranteed to be sorted, then I can always figure out where to insert an unsorted value, like this 2 here. All I have to do is walk the entire sorted partition and find the place where it fits between two sorted values. So I know 2 is less than 5, so 2 has to come before 5. And since there's no more values coming before 5, 2 is just going to take the place before 5. So here I'm going to shift 2, I will shift the value 2 over to place before where 5 currently resides, and move 5 up by 1. Okay, that's one step of my loop. I will repeat it one more time. Let's take a look at the first element of the unsorted partition, which is 1, and walk back through the sorted partition to determine where that 1 belongs. 1 is less than 5, and also less than 2, so it needs to be in front of where 2 is. In effect, I'm going to shift up the values 2 and 5 that are currently present in my sorted partition to make space for this 1 value. Let's keep going. My unsorted partition, the head of it currently has 4. And then we need to walk back through the sorted partition to determine where 4 belongs. 4 is definitely less than 5, but greater than 2, which means that 4 belongs in between values 2 and 5. So I need to shift up value 5 by 1 to make space for where 4 is going to be. Last but not least, my unsorted partition contains one value of 3. I need to walk my sorted partition again, starting at the value 5. 3 is less than 5, so it comes before 5. 3 is less than 4, so it comes before 4. But 3 is greater than 2, so it's got to fit somewhere between 2 and 4. What I'll need to do then is to shift up the values 4 and 5 to make space for the value 3 that I'm going to be inserting into this sorted partition. Now, you may be thinking that the step where I insert the element at the beginning of the unsorted partition into the list that composes the sorted partition is an O of n operation, because I'm going to have to shift up these elements that succeed the element I'm going to insert up by 1 index. And this certainly applies for arrays and array lists. We've talked about how attempting to insert an element at a specified index in an array list requires us to shift up all the successive elements by 1 index. If there's n elements remaining, then that of course is an O of n operation. Now this is going to take us back to that remark that I mentioned back in the README, where I said for these sort of theoretical analysis purposes, we're going to pretend and assume that all the list operations like insert or append are going to be O of 1. If we are iterating over a linked list, for example, and we reach the space between nodes 2 and 4, we can actually perform the insertion in O of 1 time. We just have to wire up 2 to point up to 3, and 3 to point up to 4, and have 4 point back to 3, and 3 point back to 2 if it's a doubly linked list. So there are circumstances where this is going to be an O of 1 step, and for learning purposes, we're going to treat them as if they are O of 1 in terms of cost. Now let's talk about the overall runtime cost for all of insertion sort. To look at the head element of the unsorted partition is O of 1, but to find the location in which it belongs is O of n. Consider the extreme case, where I don't have very many elements left in the unsorted partition and I'm moving them into the sorted partition. In the worst case, I have to take the head element of the unsorted partition and walk the entire sorted partition to go find its location, which is up to n steps. I do that procedure for every element inside the list, is that I walk the entire sorted partition to go find its location. Well, up to the entire sorted partition. N elements in the list, up to n steps to determine its location, gets us n times n, which is big O of n squared. An interesting observation to make here is that insertion sort is a lot like selection sort. In both ways, in both sorting algorithms, we are taking an element and sort of finding its proper location and then shifting elements around in order to place that element at the correct location. The procedure is still a little bit different though. Here, back up in selection sort, we had to scan the entire list to find the minimum element. There was no way for us to know in advance where the minimum element would be, so we had to definitely search the entire unsorted partition. With insertion sort, things get kind of interesting, where if we are looking at the head element of the unsorted partition and we're trying to find its location in the sorted partition, we could actually get kind of lucky with our arrangement. If our list is partially sorted somewhat, then we could get very lucky in that we don't have to search very far to find the correct location for the unsorted element inside the sorted partition. Therefore, it's entirely possible that we don't actually consume the O of n cost to look at and find its correct location. In contrast, with selection sort, we're pretty much guaranteed to have to look up the entire unsorted partition in order to, well, we are guaranteed that we have to look through the entire unsorted partition to go validate that the element we found is indeed the smallest element within the list. So overall, theoretical runtime performance is going to be about the same, but there's also some special considerations about the kinds of inputs that we can have for insertion sort that can maybe make it a little bit faster. I've also got that written down here. Insertion sort big O performance is n squared because of the reasons we talked about. And just like with selection sort, because it's not a recursive algorithm, I only have to consume one stack frame, and I get O of 1 stack space consumption. So insertion sort and selection sort are the two naive sorting algorithms that we're learning in this class. And I do want to say that these algorithms, despite their somewhat costly runtime of n squared, are still valuable to know. They're valuable to know because of their simplicity. They're easy to write. I imagine all of you can write a selection sort or insertion sort given a decent amount of time without having to actually go read an algorithms book to help you figure this out. The actual step-by-step process for these two algorithms are pretty intuitive. Another thing to keep in mind is this big O of stack memory is actually quite useful in certain applications. If you are writing software for embedded systems where you have very limited stack space, it can be kind of nice to know that your algorithm is not recursive and it's not going to scale based on the size of the input when it comes to stack space usage. Granted, we still have this n squared performance, which isn't really great, but we would rather spend a little bit more time running algorithm than running out of space for our entire program. Now let's turn to some optimal sorting algorithms. I say optimal in the sense of optimal performance. These sorting algorithms will actually run in n log n time rather than n squared time, and we're going to discover how that's possible very soon. Merge sort is an optimal performance sorting algorithm that uses recursion and merging to construct a sorted list out of several smaller sorted lists. We will focus on merge sort in this class because I think it's easy to understand and write compared to other optimal sorting algorithms. To get there, we're first going to learn about merging. Merging, which is not a formal term, is the technique of taking two sorted lists and combining them into a single sorted list. This can be done in O of n time, linear time, where n is the sum of the length of the two lists. Here's how we do it. We take those two lists and we examine the front element of both lists. We pop the smaller list element of the two and move it onto the sorted result. We're going to repeat that process over and over again. So we're going to look at the two lists, we'll look at the first element on both, and we'll take the smaller of the two, remove it from the list where it belongs, and place it to the end of the sorted result. Then, eventually, we're going to empty one list, and there may be more elements remaining in the other list. Once we get to that point, we're going to take the entire remaining list and append that to the very end of my sorted result. That's going to give me give me one list that is composed of all the elements of the original two sorted lists in sorted order. How does this work? Well, steps 1 and 2 are going to constantly be pulling the smaller of the two elements among the two lists. Once we exhaust one list completely, we're guaranteed that whatever elements remain in the remaining list are larger than the elements that we have grabbed so far and placed onto our sorted result. We know that's the case because otherwise we would have taken one of those elements from that list while we were processing these first two steps. So when we're done exhausting all the elements of one list, we can simply take the remainder of the remaining list and append that to the end of my sorted result to compose a single list that has all the values in sorted order of the two lists that we had to begin with. Let's go take a look at the whiteboard for a step-by-step example of this procedure. Merging, the process of taking two sorted lists and merging them into one. Merging tells us to examine the front of both lists, pop the smaller element of the two onto the sorted side, and then repeat that process until we're done. So here's two unsorted lists. I've got 1, 2, 5, 7, and 8, as well as 3, 6, 7, 9, and 9. Merging tells us to look at the first element of both lists. Here I have 1 and 3. 1 is, of course, the smaller of the two, so go ahead and take 1 and put that to the end of my sorted list and pop that off my sorted list input. Next, I look at the values 2 and 3, and once again, this upper list has the value I'm looking for. 2 is smaller than 3, so I pop that off that list and add that to the end of my sorted list. Then I have the values 3 and 5. 3 is now smaller than 5, so I pop off 3 and add that to the end of my sorted list. Then I have values 5 and 6. 5 is less than 6, so I take 5 and remove it from the input list. Next values are 6 and 7. 6 is smaller than 7, so 6 comes onto the end of my sorted list. 7 and 7, looks like we have a tie. It doesn't actually matter which one we take. Let's go ahead and take the upper list by default. So let's go that. 7 and 8, 7 is less than 8, so I take 7. 8 and 9, 8 is less than 9. And then the last two elements remaining are 9 and 9 after I've exhausted the entire first list. So I pick those both and append them to the end of my sorted list. The outcome is that now we have a single list of numbers that is composed of the numbers that we had for the two lists that we had inputted into this merging technique. Merging runs in linear time. I think this is a pretty great result. All we have to do is walk both lists. We examine each element at most once, and then we have created a list that is containing all the values of the two lists in naturally sorted order. This is a pretty great result, and we're going to take advantage of the merge operation when we write merge sort. Now let's talk about merge sort. Consider a recursive sorting algorithm and the steps for writing a recursive algorithm. We write the base case. We can observe that an empty or single element list itself is already sorted. So here's our base case. If the list is null or empty, return the list right away, or if it's just a single element, return the list right away. Then we write the recursive case. If we pray in advance and assume that the function sorts the list correctly, we can use merging to combine two sorted sublists that are solutions to subproblems of my overall problem. To get one sorted list out of two sorted lists, we just combine those two halves. So here in my recursive case, what I'll do is I'll merge two sorted lists that are two subproblems of my overall list. And what I'll do is I'll just cut that exactly in half. I will sort recursively the left half of the list, and then sort recursively the right half of the list. And then we'll go ahead and pray and assume and hope that this is going to work for us. What this actually is the algorithm for merge sort. We recursively cut the list in half to break our list into smaller subproblems until only empty lists or single element or sorted element lists remain. Then, for the recursive step, we will start to merge all those sorted lists until finally the entire list has been reassembled in sorted order. Let's turn to the whiteboard for an example of merge sort. Merge sort tells us divide the list in half recursively and then merge the smaller pieces. Let's say I had this list 5, 2, 1, 4, and 3, and I wanted to perform merge sort to get the list in sorted order. Let's go ahead and split down in between indices 1 and 2. If you have an odd number of elements, of course you have to pick a location to split. So we'll go ahead and take elements 5, 2 and put those on one side and elements 1, 4, and 3 on the other side. Okay, 5, 2, it itself is a list, it's not sorted, so I need to split one more time. The outcome is I'll have two lists that have exactly one element within them each. List 2, well, the list that contains 2 is just one element list, so it's already sorted and it hits a base case. The list that only contains 5 is a one element list, already sorted and hits a base case. That means on the way back up, I can merge these two sorted lists to compose a list that is of both elements and already sorted. So taking the list that just has 2 in it and the list that just has 5 in it, merging those together gives me a list with 2 and 5. Let's go look on the other side, on the right-hand side of the original list. Here I've got values 1, 4, and 3. 1, 4, and 3 is 3 values, unsorted, so it's one of our recursive cases where I have to split it up again. I'll go ahead and split 1 away from list values 4 and 3. So 1 is going to be its own list, which is it's kind of going to live on its own for a little bit. And then the sublist 4, 3 needs to be split one more time because again, I haven't hit a base case yet. I have an unsorted list that has more than one element. So definitely not a sorted list and I need to split it up. I go and take list that contains just 4 and 3 and cut it into two lists. A list that contains just 4 and a list that contains just 3. Now I've hit my base case because I have two lists that are containing one element each, and a list that contains one element is a sorted list. I can now use that merge technique that I just learned to arrange those two sorted lists in sorted order and combine them into this single list with two elements, 3 and 4. Now that I've got these two sorted pieces, a list that just contains 1 and a list that contains 3 and 4, I can apply the merge step to both of those sorted lists to compose the list 1, 3, and 4. That gives me the sorted right-hand partition that I had originally cut out. Back to the left side, I've got the values on the left 5, 2. I had merged them into the single list with values 2 and 5, and now I can combine the list containing 2 and 5 with the list 1, 3, and 4 because these are both two sorted lists. And using the merge technique, I can get the output list that has both values combined in sorted order 1, 2, 3, 4, 5. When we look at this in terms of runtime, we can see the following. It costs O of n steps to merge because we're going to have to go look at all these elements and sort of zip them together to form this sorted list after examining all the elements within the two sorted lists that we're intaking. Eventually, we're going to merge all the elements back up to this top level merge step here, where we're going to finally get all the values back together. The act of splitting the list in halves goes up to log n operations. If I have n elements and I cut that in half, and I cut that in half, and I cut that in half recursively, it's kind of like us doing binary search again. We're cutting the search space in half over and over again. If we're splitting in half, that's kind of like the inverse of an exponent. We're cutting it in half over and over again. Log of n is the inverse of an exponent, log base 2 of n, that is. So in a way, we have big O of log of n split operations until we finally narrowed down our list into several base case components that are just lists that have exactly one element within them. So all that together, if we have log of n split operations and big O of n merge operations, that gives me big O of n times log of n overall performance for merge sort. And I've also argued in the past that n log n is much better than n squared. I've got that written down here. Big O performance is going to be n log n. One thing that's new, though, is big O of stack memory. This is going to be n log n as well. And you can do a little bit more reading about this online, but the short explanation for this n log n stack memory cost is that it is recursive, and it's likely that we'll need O of n auxiliary memory for every single merge step. It is kind of difficult to do a merge in place. This is something that we're going to make possible, or we're going to make efficient by using a supplemental structure as extra space we can use to perform the merge. So we do have to consume a little bit more room. And you can imagine the log n portion comes from the recursion of cutting down the list into halves until they finally reach list elements that are just one element each. So overall, what we see is we've traded some stack space cost. We've gone from O of 1 to n log n stack space cost from those naive algorithms for the benefit of perhaps dramatically faster performance, where I've replaced the n in n squared with log of n to get n log n overall performance, which for large n is going to be much, much faster in terms of speed. As an exercise, you will get to implement merge sort on your next project, so watch out for that soon. The second optimal sorting algorithm that we're going to be learning in this class is called quicksort. Quicksort is a popular optimal, on average, sorting algorithm that uses recursion and a pivot value to divide the list into partitions. Our first step is to decide on a pivot value inside the list that we're sorting. As an example, we could just go ahead and pick the last value in the array as a pivot. The next step is to partition the list so that all elements before the pivot are less than the pivot, and all elements greater than the pivot are after the pivot. Then we will recursively quicksort the two partitions that surround the pivot on the left and the right sides. Let's take a look at an example on the whiteboard. Alright, quicksort tells us to pick a pivot element, some element within the list, and then organize our list around the pivots recursively. So let's suppose I had a list 5913764, which is of course unsorted, and my pivot strategy is just going to always pick the last value inside the list. Okay, the first number I examine when it comes to arranging my values around the pivot is 5. It's the furthest value on the left and the first value in the list. 5 is going to come after the pivot because 5 is greater than the number 4. So I need to arrange this value 5 such that it comes to the right of the value 4 before moving on to the next step. Now, this act of actually arranging the value 5 to occur to the right of the pivot 4 is actually a special sequence that can be done in O of 1 time. What we can do is we can intend to move the value to where the pivot currently resides, and then shift the pivot over by one index to the left. That's going to make space for the value we're trying to insert. So 5 is going to take the place of where the pivot currently resides, which is 4 at the very last element of the list. And then we're going to move the pivot from its current location into one index to the left. Now, that also means there's going to be a value that we have to think about and move elsewhere to make room for the new pivot location. That value in this example is 6. And because 6 is an unprocessed value, it's a value I haven't seen yet, what I can do is I can actually safely move it to the original location for where the value I had moved originally had existed. Again, I want to move the value 5 into the position where 4 currently resides, because 4 is my pivot. To make room for that, I'll move my pivot one index to the left to the space where 6 currently resides. But of course I have to move 6 somewhere else in the list. Because I haven't yet arranged 6 to be in its correct location based on the pivot value, I can move 6 back to the front of the list where 5 used to be, which is the value that I initially moved, so that I can examine it in the next step. And then when we reach this next step, let's go walk through this one. I have to go look at this value 6 because I haven't examined it yet. And what I'll do is compare 6 to the pivot value 4. 6 is of course greater than 4, which means I need to move 6 beyond the pivot. Once again, I'll use the same swapping strategy. I'll move 6 to where 4 used to be. I will move 4 one index to the left, and I will swap that space to the left of 4 with the space that was released by the value I just moved. So 7 is going to take the place of 6, 6 is going to take the place of 4, and 4 is going to move 1 index to the left. Okay, I haven't yet encountered another index that I have to move into when it comes to values I haven't rearranged yet, so I have to go look at the 7 here. The 7, I have to compare it with 4, which is our pivot value. Once again, I'll do the swapping process. I will move 7 to where 4 will no longer be by shifting 4 one index to the left and moving that destination index for the pivot, that value there, to the front of the list. So here we go. 7 takes the place of where the pivot is. The pivot moves 1 index to the left, and the value 1 index to the left of the pivot gets swapped into the space of the original value that I moved. So now my list is composed of 3, 9, 1, 4, 7, 6, 5. And you can start to see that the pivot is starting to form the two partitions where I have values that are smaller on the left side and values that are greater on the right side. Of course, this 9 is in the wrong place, but we're actually still technically looking at this 3 here because we haven't yet moved on. And when I look at this 3, and I assess that it exists before the pivot, which is because 3 is less than 4, I don't actually have to move 3. And this is the first time I actually get to move my reference forwards when it comes to values I have examined so far. So now that I've recognized that all values to the left, including 3, or to the left of 3, including 3, are less than the pivot, I don't have to keep looking at those, and I can move my index forward by 1 when it comes to values that I'm examining for rearrangement. So knowing that 3 belongs to the left of the pivot, I don't have to do anything, which allows me to move on to value 9 here. 9 is of course greater than the pivot, which is 4, so I need to swap 9 with 4, 4 one index to the left, and then the value that was displaced to the original location of 9. So 9 is going to take the place of 4, 4 shifts 1 index to the left, and then the value that's displaced gets shifted to the original location that got moved. That moves 1 into the space where 9 used to be, but 1 is less than 4, so it's actually in the correct location. And now that the values I'm examining have reached the pivot location, I'm done. All the values to the left of the pivot are going to be less than the pivot value, and all the values to the right of the pivot should be greater than the pivot value. Okay, so after we've completed our first pass of moving our pivot sort of towards the center and rearranging all the values to the left so that they would belong on the right side if necessary, we now have two lists on both sides that are unsorted, and we need to perform quicksort recursively on these two partitions. So I have a partition that contains the list values 3 and 1, and a partition that contains the list values 9, 7, 6, and 5. The pivot itself is going to stay in the same place, because again, all the values to the left are going to be less, all the values to the right are going to be greater, so it's actually in the spot that it needs to be. Okay, let's handle the simple case on the left side first. I have a sublist with values 3 and 1. Let's do quicksort. By selecting a pivot value, we will use the default strategy of picking the rightmost value in the array, and then we examine the value on the left, which is 3 here, because that's the first value I have yet to examine and compare against my pivot. 3 is greater than 1, so I need to swap 3 and 1 so that 3 takes 1's place, and then 1 shifts into the location that was given up by 3. So now that's going to give me a list that contains two elements, 1 and 3, that's actually completely sorted, because the next value I'm going to examine is the pivot itself, so I know that I have finished rearranging the values to the left of the pivot. Now let's go look at the values on the right. 9, 7, 6, and 5 is my current list. Let's go ahead and pick 5 as my default pivot value, and start looking at the first element on the left side of the pivot. 9 is greater than 5, so I need to swap 9 with 5, move 5 1 index to the left where 6 belongs, and then exchange 6 to where the original 9 value was stored. Excuse me. Next up, I examine the value 6, which just got moved into there. 6 is greater than 5, so 6 needs to move where 5 belongs. 5 needs to shift 1 index to the left where 7 currently resides, and 7 is going to shift into the original location where 6 had come from. Next, I look at value 7. 7 is compared against value 5, which is our pivot. 7 comes after 5, so I need to swap 5 and 7. Finally, when I start to examine the pivot value itself, once again, I know that all the values to the left of the pivot have been processed, so that the remaining partitions surrounding the pivot just need to be sorted recursively. Since there is no partition to the left of the pivot 5 here, all I have to do is recursively sort the partition containing the values 7, 6, and 9. Excuse me. So I have 7 and 6 as my left partition, and I'll pick 9 as the default pivot for this partition of the list containing values 7, 6, and 9. I need to compare 7 against 9. It is less than 9, so it's in the right location. Then I need to compare 6 against 9. 6 is less than 9. It's left of the pivot, so it's in the right location. All right, that means the sublists, the partitions that surround our pivot value 9, which includes this list containing 7 and 6 and nothing, tells me that I need to recursively now sort the list 7, 6. Okay, I'll go back to the default strategy of picking a pivot. I will pick 6 as my pivot value because it's the last element in my array. And then I will examine the value to the left, which is 7 here, and decide whether or not to arrange it to the right or to the left of the pivot. 7 is greater than 6, so we need to swap 7 and 6 in this instance. Then the next value I'll examine is the pivot itself, so I know I'm done examining and processing this sublist. The outcome of this is that once I'm done sorting all these sublists recursively, is that in place what I'm going to find as an end result is my sorted list. The clever thing about this strategy is that rather than depending on merging, as we saw when we wrote merge sort, we're instead doing the swapping repeatedly in place inside the list until eventually everything falls in line into the right order. So when I moved this 4 value up initially, and I brought it all the way down to the very bottom here in the sorted version of my list, this 4 naturally propagated towards the center when we picked it as the pivot, because during the steps when we started to process this first part of the list, we picked up on the 4 and we moved values around the 4 until it was in the right location. The same thing occurs with these other lists that were formed out of the partitions surrounding the value 4. On the right side, over here, when I picked that pivot 5, 5 naturally shifted all the way to the left into the location it belonged inside the final list, because I had to arrange all the values surrounding 5 to the right of 5. Same thing applies for this 9 value. 9 eventually got shifted up. Well, actually, it didn't have to shift at all. And we saw how, as we got the list to be smaller and smaller, the pivot that we pick sort of shifts into the right spot, and the remaining values will arrange themselves to the left or to the right of the pivot as necessary. We say that quicksort has a n log n average runtime. And we say it's average because it turns out quicksort is not always all that quick, depending on the pivot strategy that you're using. The pivot strategy that we've used in this example is to always pick the last value inside the list. This works. It gets the job done. It's very simple and easy to think about, but you can get unlucky sometimes. What do I mean by that? Suppose for a moment that our list looked like this, 9, 7, 6, and 5. And our default strategy decided to pick the value 5 here, where 5 was the last value of the list, so it was the pivot that we just picked, but it was also coincidentally the smallest value in the entire list. And what you see inside this block here is that 5 had to slowly get shifted all the way to the very front, and we had to shift all the values to the left of 5 all the way to the right of 5. This looks a lot like insertion sort, where I'm picking a value and I'm moving it all the way to the left until it finally fits in the right spot. And what we'll discover with quicksort is that we could potentially get pretty unlucky with the pivot choice and have performance degrade all the way down into insertion sort. Picking the pivot is something that actually a lot of computer scientists will delve deep into when it comes to optimizing their sorting algorithms, and there's a lot of research that goes on into picking efficient pivots. This default strategy of just picking the rightmost value is, again, something that works and it's simple to implement, but we could get unlucky in this case where we coincidentally pick the value that requires us to do the most amount of swapping. Ideally, we pick some sort of middle value, like the value 4, as we did originally, and we don't have to do that many swaps. We start to encounter values that are naturally to the left of the pivot, and those values will just remain in their respective locations. Imagine if we continuously picked a bad pivot throughout this entire process. We picked a value like 1 and forced all the values to the left, we forced all the values to go to the right, and that pivot was also very far to the right of the array, so we had to do a lot of swaps, and we ended up getting this square-like structure over and over again. The outcome of picking a bad pivot recursively over and over is that we're going to break down our list into a really big partition, then a slightly smaller partition, and a slightly smaller one recursively over and over and over again, because we're constantly picking the pivot value to the right. That is also coincidentally the smallest value among the list, so we have to shift that value all the way back into its correct location on the left side. Quicksort with a bad pivot is going to degrade into insertion sort. And that's why I have this worst case sign here. On average, we can get n log n performance, but we could get very unlucky with our pivot choice, such that we are actually picking a value that needs to be arranged in a way that every other value has to be moved around. And if we do that n times, because our partitions are not getting smaller by a significant amount, then we get n squared performance. Bad pivot selection degrades performance into insertion sort. This is a pretty interesting observation about about quicksort that we didn't see with merge sort. With merge sort, we got very consistent n log n performance because we could theorize about how many merge steps we had to do versus how many split steps that we had to do. And we were always guaranteed that we would do all those split operations as well as all these merge operations. With quicksort, on the other hand, you can kind of see that there's some semblance of luck here. With our choice of the pivot, it does not necessarily have to be the rightmost value, but it's the one I like to go with because it's simple. With our choice of the pivot, the luck factor comes into how well our values are distributed within the list and what value we just so happen to pick while we were recursively performing quicksort. Generally, we don't get unlucky. Generally, we do pretty well, but there are these worst case circumstances where you get this n squared like structure and the remaining list that has to be sorted does not shrink by a significant amount. Now I've got all those things written down here on performance. I say big O performance of quicksort is n log n. Big O performance in the worst case is n squared for the reasons we discussed. And big O of stack memory is actually log of n for each recursive call. How can quicksort be this worst case of n squared? Well, we just answered that question, which is we always pick a bad pivot and performance degrades into insertion sort because we're constantly shifting all the values over to one side of the pivot and we don't substantially shrink the size of the partitions that we have to recursively sort. We will not be implementing quicksort in this class. There is a lot of algorithmic theory involved in picking pivot and partition strategies. It is good to know what quicksort is because of its popularity, average efficiency, and similarities to merge sort. Quicksort is actually the default sorting algorithm that's used in Python and Java that comes in from the standard library. And in a wide variety of applications, it's actually the one that we see being used. It's very rare that we actually run into that worst case behavior. And there's quite a bit of research that goes into what makes quicksort good and efficient and how we can avoid having those bad pivot points being picked. With these four sorting algorithms, the selection sort, the insertion sort, the merge sort, and the quicksort, we have now cleaned out the four sorting algorithms that we are going to learn in this class. There are several more sorting algorithms that are out there in the world. You can go read about them on your own. You'll probably find them also on Big O cheat sheet somewhere. But I think these are the four most important ones. I like merge sort because it has guarantees about its runtime. There's not really a worst case like we see with quicksort. I like quicksort because it's one that you should know based on how much is used inside the industry. I like selection sort and insertion sort because they're fairly easy to remember and they're not too hard to implement. And they're especially useful when you have memory limitations that prevent you from writing things like merge sort or quicksort. And they're also much simpler, right? If you were tasked with writing a sorting algorithm for a structure that doesn't grow terribly large, then don't stress yourself out too much when it comes to writing the most efficient algorithm. Just go ahead and write one of those naive algorithms. It'll get the job done. Computers are fast enough. I do want you to remember all of these. I want you to remember the high level implementation and strategy for all of them. I would really recommend that you just keep in mind these steps that I describe in these theoretical examples. And as an extra exercise on your own, I do encourage you to try writing some of them. Merge sort is one of my favorite challenges to do when it comes to learning a new programming language. And it's one that you might actually get asked during like a programming interview because it requires that you understand some degree of recursion as well as this merge step, which is pretty cool technique and good to know because there's a lot of instances where you'll be working on, you can imagine there are instances and circumstances where you're working on systems that act on streams of data or a feed of data that involves this merge process. And now for something completely different. Recall what a queue was. A first in, first out data structure that's like a queue in real life. Maybe you're lining up to vote or lining up to get coffee. Elements that are pushed onto the queue are popped off in the same order. So whoever lines up first to get coffee gets their coffee first among all the other elements or people inside the queue. A priority queue is a queue that's going to assign priorities to every element, allowing higher priority elements to take priority over lower ones, even if they are pushed after those lower priority elements have been added to the list. Some real-world examples of this: prioritizing high-impact bugs during software development, administering aid to hospital patients according to their injuries, and serving the highest paying customers, the highest bidder. Both lists and trees offer some form of sorting. When I refer to trees, I refer to binary search trees. Could we use lists and trees, sorted lists and trees, as a backing structure for priority queues? Well, for a sorted list, we can get O of 1 access to a minimum element, but it also costs O of n average insertion. It's O of n because if we have an array list, we have to shift all the elements around in order to insert in the middle. If we have a linked list, we can't apply binary search, we have to still iterate over the entire list. For a balanced binary search tree, we get n log n performance to the min element, because it's going to be the element to the furthest to the left and deepest of the tree, the leaf node at the very bottom of the left side. But we also get log of n average insertion. In order to add on an element to the queue, we have to go find its correct location as a leaf node. So let's make an observation that binary search trees give us general log of n access to every element within the tree. But for the sake of the priority queue, we really only need access to the minimum element fast. We want to always process the patient with the most severe injuries first. We don't care about necessarily looking at all those other patients generally. We would rather just know whatever it requires most immediate attention. So that raises the question, can we build a structure that gives us O of 1 access to the minimum element and log of n insertion? That structure is called the heap. What is a heap? A heap is a special kind of binary tree that is ideal for tracking minimum or maximum values. Note that a heap structure, is different from the heap. Remember that the heap is this dedicated space in memory where object instances live and are stored. A heap structure is different from the heap. In fact, the heap, which we store instances and classes and references and other data, is not a heap at all. So it's actually a very unfortunate naming coincidence here. There's the heap structure, and then there's the heap in memory. This is kind of like heap with a capital H, and this is like heap with a lowercase h, I suppose. This is in contrast to the stack, which is actually a stack. Remember, the stack is this place where we store all those function call frames. Every time we call a function, we push on additional frames onto our stack. Every time we return from a function, we pop off a frame from our stack and pass the return value to the calling frame. The heap is not like that. The heap, we'll discover, is not actually a heap. This naming convention is indeed unfortunate. Now that we've gotten that out of the way and we're talking about the heap structure, let's talk about what that means, what the heap is composed of. Heap nodes have two unique properties that make them special. And generally, we're going to be talking about what's called a min heap. That's going to prioritize smaller values first. Something like priority 0 versus priority 1. I want to prioritize priority 0. The binary tree is going to have these following properties with every node. Every heap node is at least less than or equal to its children, if there are any children. And the heap, the tree, is complete. Every row of the tree is filled except for the bottom row, which is composed of leaf nodes, which is filled from left to right. When I say filled, I mean that it's filled out. There's no gaps in the tree. There's no point where we have several rows and then on maybe the second row there's an empty spot and then on the fourth row there's an empty spot. That's not going to happen with a heap. We're going to say that every row is completely filled except for the bottommost row, which we will fill up from left to right. Let's go visit the whiteboard to see an example of these rules in action. Here is my binary tree that is also a heap structure. My two rules tell me that every node is less than or equal to its children and that the tree is complete. So we're always going to push new nodes onto the bottom, furthest to the right where there's an empty space available. Here I see the root node 2 is indeed less than its children 3 and 4. This node 3 is less than its children 5 and 7. This node 4 is less than or equal to its children 4 and nothing. And the tree itself is also complete. There's no gaps in the tree except for at the bottom row, there's a space to the right of all the nodes that are present on the left. This completeness property, that the tree is completely full and there's no gaps, is actually going to enable heaps to be stored inside array structures. Take a look at the breadth first search ordering of walking this queue. Suppose for a moment that we started at the root, we performed a breadth first search, so we did values 2, 3, 4, 5, 7, and 4, where we go one layer out at once and we go from left to right. That gives me the values 2, 3, 4, 5, 7, 4 that I can actually compactly store inside this array. And given that the tree itself is complete, we can actually pretend this array is like a tree by using indexing to refer to the different children of other indices. Take this example. Let index 1 be the root node. So we're storing value 2, which is the root, inside index 1 of the array. We'll go ahead and ignore index 0 for now. For any given index I, the left child of that index is at I times 2. So index 1, which contains the value 2, 1 times 2 gets me index 2, which contains the value 3. And we see that that is indeed the left child of the root node. This also applies recursively. Index 2 contains the value 3. 2 times 2 gets me index 4, 0, 1, 2, 3, 4, which gets me to the value 5. Once again, 3 is the parent of value 5, and value 5 is the left child of parent 3. So this clever effect of doing a breadth first search and getting this very specific order gives us indices that will line up in a very nice mathematical fashion. It's possible because we know the tree is complete. Every node is going to have 2 nodes for its children. In that sense, when I double the index of the node I'm currently on, I'm going to jump to the next node that is in the next layer of the tree. We see the same thing apply to right children. Just like how left children are at I times 2, right children are going to be at I times 2 plus 1, which makes sense naturally. If the left child is at I times 2, plus 1 gets us one node to the right, which is the right child. We can see this in action where node 3 lives at index 2. 2 times 2 is 4 plus 1 gets us to index 5, 0, 1, 2, 3, 4, 5, which has the value 7, the right child of 3. Finally, given an index, we can reach the parent of that node with the floor of I divided by 2. So back to this index 5 example, if I'm at index 5 inside my array, which has value 7, I can get back up to value 3 by dividing 5 by 2, which gets us 2.5, and then taking the floor of 2.5, which gets us 2, which takes me to index 2, which has the value 3 inside. So this is a pretty neat effect of having this completeness property, and what that means is, in practice, when we write heap structures, we're actually going to do it inside of an array. We're going to treat this array as if it stored a compacted tree, and we're going to get actually more performance out of the values inside the array than with the values inside the heap, because there's no extra amount of referencing and moving around references that we have to do. To build a heap with tree nodes means we have to have a bunch of node structures that have left and right fields. To build a heap inside an array means we just have to fill out the array indices starting from index 1. Now let's go over the process of inserting and removing elements from the heap. Remember that the heap is meant to be the backing container for a priority queue, so inserting an item into the heap is like enqueuing a new item into our queue, and removing items from our heap is as if we were dequeuing an item from our queue. The rules for insertion are as follows. We're going to add to the very end of the queue, or the end of the heap, that is the bottommost row, furthest to the left where there's a spot available, and then we're going to bubble up that newly added element by swapping it with its parent node until the heap becomes valid. Remember, the heap rule tells us that every node needs to be less than or equal to its children, so we're going to perform the swapping process until we meet that rule and that the entire heap becomes valid. So in this example, I'm going to add the node 1 to my heap to the bottom right, because that's the first available spot in the bottom row, furthest to the left. I see that the heap rules are violated because 4 is a parent of 1, so I'm going to swap nodes 4 and 1, such that locally, 1 is no longer violating the heap rule with 4. However, we'll also see that 1 now violates the heap rule with its parent, which is node with a value of 2. Once again, I'm going to perform a swap operation. 1 is going to swap its location with 2, which takes 1 all the way up to the root node. And here, the bubbling up process is actually complete. As soon as the rules are met for the node that we're inserting, then we're done. The node is now in its correct location relative to all the other nodes within the heap. The removal process is kind of like the opposite of insertion. We're going to take away the node at the root, because that is the node of the highest priority, and then we're going to start bubbling down the node that is currently in the bottom right position. We're going to do this using this process. We will replace the root node after we've removed it with the node at the very bottom and furthest to the right. Then we're going to bubble down that node by swapping it with smaller and smaller children until the heap becomes valid, breaking ties to the left. So let's say we had this heap structure with 1 at the root, and we had removed the 1 node. We are now going to replace it with 4, which is in the bottom row, furthest to the right. And then we'll see that the heap rule is no longer valid, because 4 is not less than its children 3 or 2. So then I'm going to swap 4 with its smaller child, which is 2, and then check again the heap rules. Here we see 4 is indeed less than or equal to its children, so now the heap rules are met, and the removal process is complete. The pretty amazing thing about the insertion and removal process is that it keeps the heap rules intact, even though we don't have to traverse the other side of the tree. When I insert this 1 node, because all of my insertions into the heap are following the same set of rules, I actually only really have to check the path from the node I've inserted all the way up to the root. All the other nodes that are currently present in the heap will have already met their necessary heap conditions. We see a similar effect occur when we remove items from the heap. Once we take away the root element, which is the smallest element in our heap, and we exchange it with the bottommost furthest to the right element, we are then forced to bubble that element down until the heap becomes valid again. When we start to bubble down and we swap with the smaller child, what we'll see is that the smaller children nodes are going to naturally propagate all the way up to the top. This in a way forces the heap to restructure around what node is going to become the next root, which needs to be the smallest node within the entire tree. What we find that's a great advantage of this heap structure is that accessing the minimum element within the heap is always going to be O of 1. All we have to do is look at the root node of the tree. We're going to maintain those two heap properties, that is, that parent nodes are always less than or equal to their children and that the heap is complete, via those two special insertion and removal procedures that we had just discussed. I've gotten those formally written down here. When we insert, always insert to the bottom row, open spot, farthest to the left, then swap that node with its parent until the heap property is fulfilled. This is a process known as bubbling up. When we remove the minimum element, the root node from the heap, we're going to swap in the leaf node farthest to the right, that is at the bottommost row of the heap, into the root position. Then we're going to bubble that node down, swapping repeatedly with its smaller child until the heap condition is fulfilled. If the children are tied in value, we want to prefer the left child. Otherwise, we can actually get into circumstances where the heap no longer becomes valid. I'll leave that as a thinking exercise on your own to figure out how you can draw a heap where we somehow violate this rule by swapping with the right child instead of the left child when there's a tie. An interesting side effect of that completeness property with the heap is that we can efficiently store heaps inside of arrays, which we had saw on the whiteboard. If we do so, we can place the root element at index 1, then we can refer to any index. We can refer to any index's left child by multiplying that index by 2. We can refer to any index's right child by multiplying that index by 2 and then adding 1. And we can get the parent index of a given index by dividing that index value by 2 and taking the floor, or rounding down. Excuse me. Now let's analyze the performance of your heap. Min element retrieval, O of 1, great. Min element deletion, log of n, because at most we have to propagate the bottommost elements that we had swapped into the root location all the way down to the bottom again. New element insertion, worst case, log of n, because we have to insert an element and potentially swap it all the way back up to the root. New element insertion average, O of 1. This may be a surprising value to some of you. How can new element insertion be on average O of 1? And this is not necessarily immediately intuitive. We've learned that even in the case of a balanced binary tree, we will have to potentially traverse all the way from the root node to the bottommost row of the tree, which is log of n. On average though, with a heap, based on the distribution of elements within the heap, we can actually get really good insertion performance. Remember the process for inserting, this bubbling up process. I add an element to the bottom, and I slowly bubble it up all the way to the top. When I actually add an element to the bottom row of the heap, every step on the way up, I ask this question of whether or not that node is less than or equal to its parent node. And I do that over and over and over again until I finally, in the worst case, in terms of performance, reach this root node. But because of the way the heap is arranged, what we're going to end up seeing is that bigger numbers tend to process and stay at the bottom because they can't be replaced. They can't replace their parents, and smaller nodes are going to end up at the top. So the clever thing about how heaps are designed is that because there's so many nodes at the bottom, the heap is going to have way more nodes towards the bottom rows than it will towards the top. The heap is by nature a binary tree structure. Every single row has twice as many nodes in it as the previous row. So when I bubble up a value onto its parent, it's almost as if I'm comparing that value I'm bubbling up against all of its neighbors. This is not an exact comparison, but it is one way to sort of intuitively understand how, on average, you don't actually have to bubble up very often. This bubbling up step is essentially like saying this node belongs in a hierarchy level that is above all the other neighboring nodes, and all the other nodes it's already surpassed. Because the tree is very heavily weighted towards the bottom, there's going to be twice as many nodes with every row that we go down. On the process of bubbling up, this node essentially has to beat out all of its neighboring nodes in terms of its value on its way to the root. With that in mind, if we have a roughly even distribution of elements inside of our tree, these values tend to not bubble up very far. What is the likelihood that this value needs to bubble up? Well, if it's less than its parent, then in a way it's like saying this value is less than all of its neighbors. Now, that's not a guarantee, but it's generally pretty close. That gives me, let's say, a 50% chance of needing to bubble up if I have an even distribution. Then on the next layer, I have to ask again, is this node less than or equal to its parent, which is kind of indicative of whether or not it's equal to the other neighbors in that row, and if so, I'm going to keep bubbling up. It tends to be something like 50% chance with every single bubble up procedure. And if I have a tree with at least some number of depth in it, then those 50% odds are going to shrink over time. If I start at the very bottom, it's 50% chance to swap up, then there's another 50% chance to swap up that, and then so forth, and it's very unlikely that it gets very far. So half the first time, half the second time, that gives me a quarter chance. Half that gives me 12.5% chance, and so forth. The outcome is that, given a roughly even distribution, we don't actually have to do that much swapping. In general, the insertion process only does about 2 swaps or so before that node is actually in the position it needs to be. That gives us a really effective insertion and removal for priority queue. In the worst case, even, it boils down to log n, which isn't so bad. This structure is therefore ideal for a priority queue. We talked about our needs in how we wanted efficient insertion and efficient removal. And we discussed how the other structures that we'd explored so far, the binary search tree, the sorted list, those don't give us those ideal O of 1 operations. Here, we can get the best of everything. We can get O of 1 retrieval, log of n deletion in the worst case, and O of 1 on insertion average, which is better than our average insertion of log of n for both the list that was sorted and the binary search tree. Why don't binary search trees share this optimal behavior? Well, we've talked about how binary search trees are structured. Another way to intuitively understand why binary search trees are a little bit slower for the sake of building a priority queue is that binary search trees have to represent a more general structure. The heap is meant to fulfill a very specific purpose, which is always having a minimum element at the root node. The binary search tree is instead meant to store a general set of data that we then look up into later. For example, a very large tree of people in a database. The binary search tree would be appropriate for, because maybe I have to look up person X, person Y, person Z, and the binary search tree is arranged in such a way that it's very efficient for me to look up any number of one of those people. The heap, on the other hand, doesn't care about the other nodes that are not the highest priority node. It's ultimately the root node that matters most to us. It's the patient that requires the most care, the most urgent care that we have to take care of first. That's why the heap is so good at these priority queue-like operations, is because it's designed around fulfilling that need, not this more general purpose of being a structure that can be searched, like the binary search tree. Okay, that's a lot to take in for today. As always, I encourage you to download these notes, check them out on your own time, maybe try the implementation on your own for these algorithms and structures that you've learned today. Thank you for listening. I'll catch you next time.